Welcome back, everyone. Welcome to our module on coordination. In the in-class session, I do this kind of as two separate modules, but we're kind of squish them together today. And so we're going to learn about coordination both from a cognitive psychology standpoint and from a cognitive neuroscience standpoint. First off, coordination. Now, a lot of research on human movement is reductive. It simplifies the challenge to be able to make it easier to understand. And we talked about, for example, studies where we look at just the extension of the arm. And we can learn a lot from those, but they're not very realistic to real world movements. And that's where coordination research comes in. We want to understand, well, how do we coordinate our entire body, because that is more common than, say, us walking around and moving just with elbow extension to our target. So how challenging is it to coordinate our body? And then what is different about coordinating multiple limbs, joints, muscles compared to just some of the reductive research that looks at very simple movements? There are many types of coordination. We coordinate our entire body when we dance. We can talk about the coordination between hand and eye, which is very common in sports. There's coordination between individuals. So this is kind of the classic example in joint action research, where we talk about coordination between people, where two people working together to lift a couch. But this is obviously applicable to, say, factory workers working together on an assembly line. And finally, there's a coordination of the two hands, which we'll see more of today. Now, this is a picture of what was later called Picklegate, and this was when Hillary Clinton was running for president, so quite a few years ago now. And there were some questions about her health. She, at the time, was older, I guess not as old as she is now, but there seemingly is always questions about the president's health, because our presidents and our candidates for president are often older individuals. So kind of jokingly, she went on Jimmy Kimmel and demonstrated her vitality and her physical health by opening a jar of pickles, which is notoriously hard to do. And this kind of went wrong. It went downhill from here because some people on Reddit said, well, when she opened the pickles, it didn't make a pop. And they surmised that maybe someone had pre-opened the pickles to make it look like she was stronger than she is. And Jimmy Kimmel, what he did is he then posted a follow-up video, kind of in jest, to explain what had happened. And he had the pickles, and he went to see Guillermo, and he said, Guillermo, Hillary's going to be here tonight. I need you to protect these pickles. Don't let anyone open them. And Guillermo said, yes, boss. And then as soon as Jimmy left, Guillermo opened the pickles. And that was the supposed explanation to why they didn't give a pop when Hillary Clinton later opened the pickles, on the show. So this was all kind of joking and in jest, but very likely the reason why Hillary did not win the presidency. So joking aside, let's get to a more important question of how challenging is it to coordinate your muscular system. Now, we all do this. So after this video, you'll likely get up, you might walk somewhere, and to do that, you are coordinating your muscular system. And walking is somewhat challenging, but we can also do more complicated things, like think of playing a sport, dancing, or a musical instrument. There's a lot of coordination going. So how hard is this? Well, what we can do is we can think about what are we controlling, and we are controlling our muscles. Now, we have about 650 named muscles. There's probably more than this, but let's just say we have about 650 muscles. But we don't control muscles individually. So if I want to, flex my arm, my bicep activates, I'm not simply turning all the bicep on and off. What we're controlling are motor units. And there are multiple motor units to each muscle. Actually, let's see, I have some stats here. So it depends on the muscle and the function. But let's see, the first dorsal interosseous, so a very small muscle in your finger, has 119 motor units. Now the bicep that I just mentioned has 774 motor units. So a muscle can have more or less motor units. But let's go with that on average, maybe we have about 300 motor units per muscle, and that's probably a decent estimate. So we have these 650 muscles, we have about 300 motor units. That gives us 1,900, let's get this right, 100,000, why am I struggling with this number? 195,000, there we go, 195,000 total motor units. So to be able to control all the body, not necessarily controlling all motor units at one time, but if I want to be able to control the full complexity of my motor system, I need to be able to control 195,000 total motor units. And that's a lot. That's likely very challenging for the mind and brain. Now it turns out when we want to send a signal to a motor unit, there's not a straightforward control. So if I always send that same signal down to, say, one of my bicep motor units, it's not always going to produce the same amount of force or have the same effect. If it did, we would say that we have straightforward control. Now control is not straightforward for at least 3 reasons. We're going to talk about the anatomical context, the mechanical context, and the physiological context. And the first 2 you've likely seen before in some of your other kinesiology courses. All right, anatomical context, and this will probably be reminiscent of some of your anatomical kinesiology. Now the role of a muscle is context dependent. And the deltoid example is kind of my favorite one out of these 2, so let's talk about it. So let's say I have my arm up and I want to lower my arm slowly. So we're talking about this first example. To do that, my brain very cleverly realizes that, oh, I can do that with an eccentric contraction of my deltoid. I'm just going to slowly lose out to gravity. Now let's say we start in the same spot and we want to end in the same spot, but instead of getting there slowly, we want to get there fast. Well, my mind is smart, as is yours, and it realizes that, well, I can't just lose out to gravity. That's going to be too slow. To be able to do this fast, I need a concentric contraction of my lats. So what we are seeing here is that what seems very similar, these 2 movements in which to a robot, if it just said, okay, starting position, ending position, a robot might do this exactly the same way. But our muscles are context dependent, and we need to consider, where is the body, what is the goal, do I need to get there slow or fast, and that will change which muscle is activated and when. In this other example, what they're showing here is that the pectoralis major, its impact or its movement will depend on the position of the body. So if you're standing with your arm at your side, kind of an anatomical position, the pectoralis major will largely be an internal rotator of the arm, which is fine. If you need to do some internal rotation, great, you can use your pec. But if my arm is at the side and now I contract my pec, well, it's going to be a very different action. It's going to maybe do some abduction rather than internal rotation. And the mind needs to be aware of that. So it's not just simple as this motor unit does this action. No, it depends on the anatomical context. The other thing that's important is the mechanical context. So the relationship between muscle activation and force depends on the mechanical condition. So if I go back to my bicep, and if I send a signal down to some of my motor units here to contract, I'm at a fairly optimal force-length relationship. So that signal will produce a higher level of force than if my arm were fully extended and I'm at a less optimal force-length relationship. And the mind and the brain need to consider these factors, that signal will not always produce the same amount of force. It depends on the force-length relationship and the force-velocity relationship. Lastly, we need to think about the physiological context. So when I send a signal from my brain to my motor unit, we think of this pathway, one of those being the corticospinal tract, as sometimes being this passive wire. I send the signal, it travels down the wire, it arrives at the destination. But in reality, this cortical spinal tract is not just a wire, but it can have various levels of excitation and inhibition throughout the pathway. So my cortical spinal path could be more excited in one situation. Let's say I'm well rested, maybe I've had some caffeine, maybe I'm playing a sport and everyone's cheering me on and I'm in the zone. This pathway is going to be very excited. And if I send the same signal down that I'll do repeatedly, because this pathway is more excited, I'm going to have a larger impulse or a larger amount of force produced by my motor unit. Now this pathway can also be inhibited. Let's say I'm up late, so I'm mentally tired. Maybe I just ran a marathon, and I'm physically tired. Let's say I haven't had any caffeine, and maybe I'm in a bad mood, or maybe I'm losing a game of basketball and kind of grumpy about it. So this pathway, so my muscle, that could be tired as well, but just this cortical spinal pathway can be more inhibited. And the mind is going to have to realize, okay, well, I'm going to send a signal, but what is the state of this pathway, the physiological context? Because if it's excited, well, then I can decrease the signal I send. But if it's inhibited, maybe I need to increase that signal. So control of our motor units is very complicated. To summarize, we have 195,000 total motor units. That's a lot. If I were to go over to engineering and say, I want you to build a robot with 195,000 motors or actuators, they would say, oh, that's a big challenge. They're not going to be able to do that in a weekend. And the other problem, and this is more complicated than what we'd see with a robot, because with a robot you would send a signal and the same action would happen every time. But the role of these 195,000 total motor units will depend on the context, the anatomical, mechanical, and physiological context. So coordinating the motor system, we all do it. Right now I'm standing, I'm controlling many of my motor units successfully, but I think we can agree that this is a complex challenge for the neuromuscular system. So once we understood that, yes, this is a complex challenge, motor behavior researchers began to question, well, how do we simplify coordination? As I'm standing here, it would be way too much to try to coordinate all 195,000 motor units. So how do we simplify this coordinative challenge? What we found, and we'll get to some of this research, is that we constrain our degrees of freedom. So I have 195,000 motor units. I'm not going to control them all simultaneously. I'm going to constrain those degrees and only control a few at a time. So we reduce the degrees of freedom by constraining them. Now let me give you an example, a real-world physical example. So not a motor system, but think about a car. So a car has 4 wheels, and the most complex car, or the car with the most degrees of freedom, you'd be able to control each wheel independently. So imagine having 4 steering wheels, maybe 2 for your hands, 2 for your feet, and each hand would control 1 wheel. So you could have the front wheels go opposite directions, the back wheels do the same thing, do the opposite thing. That would be 4 degrees of freedom. Now that would be hard to control, right? 4 steering wheels, that's a lot to keep track of. But the car would be very maneuverable. If we turn all 4 wheels in the same direction, we would be able to turn in a tighter circle than we can normally. So that would be too hard to control, those 4 degrees of freedom. So think about kind of like controlling 195,000 total motor units. So what we do with cars is we go from 4 degrees of freedom to 1. So back wheels, we say, you're just going to be straight all the time. So those 2 degrees of freedom are gone. The front wheels, there could be 2 degrees of freedom, but what we do is we say, okay, you're going to be able to move, but you're always going to be locked together. So instead of being able to do, this, control them independently, they're now locked together. So imagine 4 degrees of freedom, every wheel can do whatever it wants. The back wheels are locked, they don't turn at all. The front wheels, when they do turn, they're going to turn together. So we've gone from 4 degrees of freedom to 1. So we've got a car with 1 steering wheel, which is far easier to control. And we're going to look at how we do that with the motor system, how we constrain our degrees of freedom. Now, lots of research has shown that we constrain our degrees of freedom when learning new motor skills. And there's kind of 2 famous examples of this. We can look at a toddler learning to walk, and we can also look at a young adult or any. So we'll ignore kind of when maturation has a huge impact on our motor skills. So children, toddlers, and older adults, and we'll look at kind of just young adults, and the example here will be learning to dance. So if you want to pause this video, you can watch a little video of my son Elias when he was about 1 and he was learning to walk. So take a look at his video, look at his gait, and then I'll tell you how he's freezing his degrees of freedom. So when babies, children, toddlers learn new skills, they don't just suddenly break out the efficient gait pattern we see in adults. And that's because it's too complicated for their mind that is still developing to control all those degrees of freedom. So they have a very inefficient gait pattern. And one thing that's characteristic is at the feet kind of just go up and down. Now, to be efficient when you walk, you really want to go heel-toe so that we can transfer the energy smoothly. But to do that, you're going to need to control more degrees of freedom in your foot. Toddlers, that's kind of overwhelming for their neuromuscular system. So they do kind of this lifting at the hips. Sorry, you can't really see it here, but they're kind of lifting their feet at the hips, not even very much bend at the knees. So we don't see that nice swing in their knees, which again is very efficient. They're just kind of lifting up and down, mostly at the hips, freezing many of those degrees of freedom. And we've known for years that this is a common strategy in children and toddlers and babies when they learn new skills. There's so many degrees of freedom, they're too hard to control, so they freeze some of those degrees of freedom to simplify the movement. Now, as their neuromuscular system learns that pattern and gets used to it, they'll begin to unlock degrees of freedom and develop a more efficient walking pattern that is characteristic in adults. So a toddler walking, is very kind of cute and adorable. They have this inefficient pattern, but the older they get, the more we start to see heel-toe, the more we get to see a good swing at the knee, and they unlock degrees of freedom to have the same efficient walking pattern that we see in adults. This is not just something we see in children. So any of us, if we started learning a new skill today, at first we would look very stiff, inefficient, maybe a bit uncoordinated, and a great example of that is dance. And I found a video, I went through lots of these 1-year progress videos to kind of find one that I thought was really good example. And this is a young man learning how to dance. And I think he's a rugby athlete. I think he mentions that at some point. So he has, a developed neuromuscular system. He's very strong, probably very good at rugby, but dancing is different. And when he starts to dance, although he's got all the muscles necessary, he doesn't know how to unlock and individually control those degrees of freedom. But check out the video of him and you'll see over a year that he unlocks more and more degrees of freedom, and we see that in him becoming more coordinated, basically being a better dancer, and it would also take less energy. He'd be more efficient at dancing, kind of like how a toddler, as they get older, becomes more efficient at walking. So give me a pause and check out that video. So within the field of coordination, we've known for a long time that we constrain our degrees of freedom, and as we learn a task, we unlock those degrees of freedom. We're going to talk about some really influential research where Professor Kelso and his colleagues found that even a very well-practiced movement, we're going to look at reaching, something we do, I don't know, hundreds, thousands of times a day, even something that simple, that fundamental, and you would think I've learned everything there is about reaching, you know, it's very easy, but I still constrain my degrees of freedom. Whenever possible, we simplify coordination. And I've said this before, you can think about it that the mind is either efficient or lazy, you know, just like, you know, we are sometimes. And whenever we need to move, our motor system always wants to do that as easy as possible, constrain degrees of freedom, and control as few as possible. So we're going to look at two famous experiments by Professor Kelso. So this first one, we're going to look at timing of movements, or the temporal coupling, and that hopefully will make sense as we go. And this is really foundational to Fitts' law. So in part of the experiment, participants with one hand would move a long distance to a small target. So recall Fitts' law, that would be a high index of difficulty, and we expect a long movement time. Over here, so I flashed by the easy target, but the easy target has a short movement amplitude and a large target width, so that has a low index of difficulty. So by Fitts' law, we're predicting a long movement time here and a short movement time here. Now these are movements with one hand. We also call these unimanual movements. And sure enough, yes, these movements abided by Fitts' law. We have a much longer movement time here, we'll say about 150 milliseconds, and a shorter movement time here, about 100 milliseconds. Now we got Kelso introduced bimanual movements, which just means you're moving with both arms at the same time. In this condition, we also call these movements symmetric because each hand has the same goal or the same index of difficulty. So here, your two arms are going to move to two difficult targets, and here both your arms move to those two easy targets. And what he found was Fitts' law. So it doesn't matter if you're moving one hand or two hands. If both hands go to two difficult targets, you have a long movement time. And if both hands go to two easy targets, you have a short movement time. So nothing abnormal at this point. Here's his critical condition. So it's bimanual, you're going to move both arms, but we call this condition asymmetric because one arm has an easy goal or a low index of difficulty, and the other arm has a high index of difficulty. So we tell participants simultaneously move to the short, easy target with your left hand and the long, difficult target with your right hand. And he did do the opposite condition where instead of doing this, you know, you would do this, but we'll just look at one to keep it simple. So what they found here is that movement time to the long target was still about 150. The fascinating result is that the movement time to the short target was not 100 milliseconds. It was much longer than you would predict from the previous conditions which abided by Fitts' law. And what Kelso said was exhibited here was temporal coupling. So instead of moving the two arms with independent timing, the two-hand movements had simultaneous movement initiation and termination even when the movements were to targets with different difficulty. So if a bimanual asymmetric movement was just the sum of two unimanual movements, we should see one be fast and one be slow. But to do that, we'd have to coordinate many more degrees of freedom. And the brain says, well, there's no real requirement of when exactly I get to these targets. Sure, I'm supposed to do it fast, but I don't have to move them independently, so I'm going to simplify it and kind of move them with simultaneous timing. And that will simplify the degrees of freedom. Let's look at that in another chart. So here's the unimanual difficult movement, and remember movement time was about 150. The unimanual easy movement was about 100. And that's just showing Fitts' law. This is normal, as expected. Now bimanual symmetric movements also showed Fitts' law. So two difficult movements, about 150. Two easy movements, about 100. Great, even when we move with two arms, we still see Fitts' law. But where we see temporal coupling, and I guess a violation to Fitts' law, is the bimanual asymmetric condition. So the arm that goes to the long target is still about 150, and that's really what we predict from unimanual or bimanual symmetric performance. So the difficult movement still takes 150. The temporal coupling occurs in the easy movement. Remember, we should be able to do this movement in about 100 milliseconds, and yet the movement time gets a lot longer to be far more similar to the difficult movement. So you've got simultaneous or near simultaneous initiation and termination of these two movements, even though they have different difficulties. And the reason for that is to constrain our degrees of freedom and to simplify coordination. And the neat thing is that we see that even though a reaching movement is hugely well practiced, I'm a reaching expert, you're all reaching experts, we all do this all the time, and yet our body still finds a way to simplify that, what seems like an easy coordinative challenge. So here's a quote from Kelso. So we believe that the brain produces simultaneity of action as the optimal solution for two-handed task by organizing functional groupings of muscle that are constrained to act as a single unit. So instead of controlling these independently, we constrain them to act together with the same timing. So we make bimanual asymmetric movements easier by initiating and turning the movements at approximately the same time. Now Kelso actually did look at the entire kinematics as they reached, and they were also coordinated. So it wasn't that the easy movement got to the target and then just waited to move down, and that would not be as coordinated. But no, the entire movement was coordinated because peak velocity, and then the peaks in acceleration were also coordinated. So we coordinate the entire movement kind of like this to simplify coordination. So that first experiment by Kelso showed us temporal coupling. Now this second one shows spatial coupling. And typically in our everyday movements, these are often occurring at the same time. So we can isolate temporal coupling, we can isolate spatial coupling as Kelso did, but in daily movements, we often have what we call spatial temporal coupling. Both are occurring simultaneously. But let's look at spatial coupling. So here's the task, very straightforward. No unimanual movements this time. He just looked at bimanual symmetric and bimanual asymmetric, asymmetric being the interesting condition. So here's a bimanual symmetric movement. You start at these two home positions, and there's two targets to the side, and you don't slide your hands, you lift them off the surface to the targets. So you're going to make a movement something like that, and you're doing it as quickly and accurately as possible. Here's some trajectories. So these are two different participants, and we can see 4 different trials. So on this trial, I wish I had 2 cursors, but you can see the right hand moves up and out, and the left hand moves up and out. So this is kind of normal, and here we see another participant. Trajectories, look pretty similar. So that's a bimanual symmetric condition, but that's kind of easy because by default both hands have the same kind of movement path, even though one's to the left and one's to the right. So this is the easy condition. Here's the harder bimanual asymmetric condition. So all they did is they put an obstacle in the path of the left arm, and they told participants that they had to go over it. So not in front, not behind, but you're going to have to increase the height of your trajectory to avoid that obstacle. So this arm, the left arm, is going to have to go higher. The right arm will move at the same time. The question is, what will happen? Will it show the same kind of low-level trajectory that we saw earlier? And really you should, because there's no obstacle here. Alternatively, maybe we're going to see spatial coupling. And because this arm goes higher to avoid the obstacle, even though there's no obstacle here, it would be easier, that require the coordination of fewer degrees of freedom, if this arm also made the same sort of high trajectory as the left arm. So what happened? So here's trajectories from kind of one group of participants, and the interesting thing is they didn't show spatial coupling. So here's the left hand going over the object, and the right hand had a low trajectory, just like bimanual symmetric trials. So some participants had no spatial coupling. Now the other half of participants actually showed strong spatial coupling. So there's their left hand going over the target, and notice the right hand. There's no target here, and yet they're lifting it up and having a huge high trajectory even though there's no object. So half the participants had no spatial coupling, and the other half of the participants showed spatial coupling. And spatial coupling, from more experiments, we've seen that it's a bit different than temporal coupling. Temporal coupling seems to be a very strong constraint that always happens. Spatial coupling is not as strong. The harder the task, so the faster we ask you to do this, the bigger the obstacle we put in your way, the more complex the movement, the more likely that we'll see spatial coupling in all participants. But spatial coupling seems to be a weaker constraint. And if you want to practice this task and get rid of spatial coupling, we can do that with, say, a moderate amount of practice. If we want to go back to the previous task by Kelso and learn to do these movements with independent timing, it's much harder and it will take extensive practice. So spatial and temporal coupling both occur, but they're a bit unique from each other. Let's summarize these two studies by Kelso. So how will people perform when asked to make bimanual asymmetric reaches? So what we see is that people typically constrain or restrict their movement in some way to reduce the degrees of freedom, which makes coordination easier. Depending on the task, we might see temporal coupling. That's a very strong constraint that we typically see all the time. Spatial coupling can sometimes occur. The harder the task, the more likely we're going to see spatial coupling. And again, why are we doing this? We're reducing our degrees of freedom to simplify coordination, even for very well-practiced movements like reaching with your arm. Just a note on terminology, because I've kind of thrown a lot of these terms out, but we're talking about decreasing degrees of freedom. Sometimes I'll talk about constraining degrees of freedom or freezing degrees of freedom, but we're going from many degrees of freedom to fewer. How does this happen? Well, it can be temporal coupling, like in Kelso's first study, spatial coupling, like in the second, and in more real-world tasks, we often see these occurring at the same time, and we call that spatial temporal coupling. A classic example of this is patting your head and rubbing your tummy, but from kind of doing coordination research for years and sometimes using that as a demonstration, I've learned to unlock those degrees of freedom. I can make it harder by switching my hands. Let's see. Oh, yep. See, now I don't do this one as much. Well, this kind of feels weird. So I am expressing some spatial temporal coupling. Ooh, another good one. This one I haven't practiced is, so it's easy to do thumbs up, fingers out, because that's a symmetric movement. But now what you want to try to do is thumb up, finger out. So alternating. And if I'm slow, I can do it. The other thing, because I haven't practiced this, is when I'm doing this movement, I'm using a lot of force to hold down this movement. So I'm not this thumb. So I'm not very efficient at it. But with practice, I've seen videos of people who practice this task. You can unlock those degrees of freedom and get as good at that as I am at patting my head and rubbing my tummy. All right, so that's kind of the cognitive psychology of coordination. Let's now talk about cognitive neuroscience. The question here is, how does our neurophysiology, the way we're wired, actually cause and contribute to spatial temporal coupling? We're going to look at two structures or two sources of coupling. We've got ipsilateral corticospinal axons, and we've seen corticospinal axons before, but this will be a new look at them. And we're going to look at the corpus callosum, this large bundle of fibers that is the main connection, not the only connection, but the main one between our two hemispheres. First up, ipsilateral corticospinal axons. So a couple times throughout the course, we've talked about corticospinal axons, and I maybe haven't even said contralateral corticospinal axons because we almost kind of assume when we're talking about corticospinal axons, we're talking about the ones that are contralateral. And by that, I mean they start in one hemisphere, So here we have our left hemisphere, and this the cortical spinal tract descends down the brainstem. It decussates. Remember, that's just the fancy word for crosses over. Then it will continue to descend to the proper level of the spinal cord to control whichever muscle we want. In this case, we're using our hand to press a button, so that would be lower cervical, upper thoracic, depending on the muscle, to press the button. And when we say corticospinal axons, we typically mean the ones that are contralateral, that decussate or cross in the brainstem. So they start in, say, my left hemisphere to control my right hand. The interesting thing is that not all of our corticospinal axons cross or are contralateral. Now, most of them are. It depends a bit on the individual, but it's estimated that 85 to 90% of your corticospinal axons cross or are labeled as contralateral. That leaves us with about 10 to 15% of what we call ipsilateral corticospinal axons. So imagine a movement here. So now we're in the right hemisphere, and let's say I want to send a signal out to contract my left hand. So the motor areas in the brain will send that signal out down the corticospinal axons, both ipsilateral and contralateral, and 90% will cross and go to my left hand and do this. But the ipsilateral ones, if I don't inhibit those, when I do this with my left hand, 90% of my motor command goes here, but 10% will actually go to my other hand. And what can happen is they can cause what we call mirror movements. So this hand will do a big movement, and then the 10% of the signal will go to my other hand and cause a mirror movement. Now, as we grow up and our nervous system develops and matures, we learn to suppress those ipsilateral fibers. So, I can do this with this hand, and even if we measure the EMG, we'll see no signals going to this hand, because I've learned to suppress those ipsilateral fibers. We can see those ipsilateral fibers produce mirror movements in two examples, and let's look at those. So first is in a neurological genetic condition called bimanual synkinesis, or sometimes more simply mirror hand syndrome. Let's find my notes about this here. So it's a genetic disorder, and instead of having kind of 90 contralateral and 10 ipsilateral corticospinal tract fibers, they have far more ipsilateral than normal. And it can depend on the individual, but let's maybe say you've got 60% contralateral and 40% ipsilateral. So now in this case, if I had this condition, when I'm doing this, it's really hard to suppress 40% of those ipsilateral fibers. Now you can learn to do that, but it's going to take far more practice. In this video, what you'll see is an individual with bimanual synkinesis. So I don't know exactly, but let's just say maybe they have 40% ipsilateral corticospinal fibers, and they're going to play the piano. So they've learned to do bimanual asymmetric movements, but it's going to take far more effort for them because they have way more ipsilateral fibers. So first they'll play with one hand, and you'll see the other hand just goes along for the ride because they have so many ipsilateral fibers. Then they'll play with this hand, and we'll see that hand goes along for the ride. And then finally, they'll play a complex song where both hands are playing independently. They've learned to do this. They've learned to suppress those ipsilateral fibers, but because they have more ipsilateral fibers than you or I, it would have taken them far more practice to be able to do the same sort of coordinated feat that someone with only 10% ipsilateral fibers could do. So give me a pause and take a look at this video. So that's kind of an extreme example, but an interesting one. The other case, coming back to my son Elias here when he was growing up, is that when we're little, when we're toddlers and young adults, we haven't yet learned to completely suppress those mirror movements, the activation of those ipsilateral fibers. And the younger we look, the more likely we can see these mirror movements. But the challenge is when we go young, like 10 months here, well, Elias doesn't necessarily understand the instructions, and he doesn't necessarily, he can't tell us what he's doing. But here, what I captured is I think in one hand, well, I know in one hand he's holding a rattle, and I think he's trying to just shake that in one hand. And what I think we're seeing in the other hand, and it's hard to know for sure, but these could be ipsilateral movements sneaking out into his other arm. Now it could also be a postural response, or you could be simultaneously activating both arms. We don't know for sure, but what we might be seeing here are ipsilateral mirror movements. So take a look at that video. Now mirror movements can be documented up to maybe even 8 or 9 years old, but the older the child, the smaller they'll be, and you might not even physically see them, but maybe if we record electromyography, EMG of the muscle, when a 7-year-old does this, we might see very small muscle activity. Now here's Elias at 3 years old, so still in that range where we might see mirror movements. And at 3 it's easier because he can follow instructions, but his nervous system is getting more developed, so it's less likely to see activation of those ipsilateral fibers. So check out this video again. I've given him a rattle, I'm asking him to shake it, and he does it, just a small movement at first, but when it gets bigger, we see the other hand maybe producing mirror movements. So ipsilateral corticospinal fibers do contribute to spatial temporal coupling. And great evidence for that is if we have more of them, well, then we see stronger spatial temporal coupling. The second structure that contributes to spatial temporal coupling is our corpus callosum. So the corpus callosum is the largest connection between our two hemispheres. There are other connections, but the corpus callosum is the dominant one by far. Now it's so big that we even have names for the subsections of it, but we won't worry about it. The corpus callosum, though, really does connect the hemispheres, the two cerebral hemispheres, in the frontal lobe, in the temporal lobe, in the occipital lobe. It connects, both hemispheres from front to back. Now, I like this image here because when we see these, we kind of think, okay, there's a bundle of fibers, but remember those axons are spreading out into the hemispheres. So you can see, them connecting the two hemispheres of the brain, all the way from the frontal lobe way back into the occipital lobe. Now, the corpus callosum, we know that it contributes to spatial temporal coupling because we can look at individuals without a corpus callosum. Before we get there, let's look at a control, neurologically intact individual, someone with a normal corpus callosum. So if we ask them to draw two shapes at the same time, and this would be a bimanual symmetric condition because both arms are doing the same thing. So that's easy because by default we want our arms to be spatially and temporally coupled. Easy to do that. But if I ask someone to draw two different shapes at the same time, so this arm needs to do this, which on its own is easy, the other arm needs to do that, but at the same time the spatial temporal coupling caused by ipsilateral fibers and the corpus callosum are going to make that hard. So let's see if I can, it just doesn't work. I can't I can't do that. You get a lot of coupling and you make a mess. Now here is someone without a corpus callosum. Now how might you not have a corpus callosum, or what are ways that you might lack a corpus callosum? So there's two common ways. So first of all, it's possible that during development in utero, that because of some sort of disturbance, you are born without a corpus callosum. This is rare, but it can happen. Now most commonly, if there's some sort of disturbance in utero, there will be several issues. So there could be many development issues, and lacking a corpus callosum would be one of them. And if that occurs, there very obviously be many issues. Very rarely it's possible that the only issue is that you have no corpus callosum, and if that occurs, the doctors won't even notice. You'll kind of mature, develop as a normal individual, and you might never know that you have no corpus callosum. And this happens to some people. It's very rare, but maybe one day, you know, they're having headaches and they get an MRI, you know, for some other reason, and then they find out, oh, you've got no corpus callosum, which is kind of cool. So that can occur very rarely. The other way, which I guess is also rare, is some people actually have surgery to cut their corpus callosum. The reason this is rarely done is to help epilepsy. So it's not standard treatment for epilepsy. There's lots of medication that can help epilepsy. But if you are resistant to medication and your epilepsy occurs in a predictable way in that it begins in one hemisphere and then it crosses the corpus callosum and then goes to the other hemisphere. If that's your type of epilepsy, then we can actually cut the corpus callosum, and when you have a seizure and there's epilepsy in one hemisphere, it won't cross the corpus callosum because it's gone, and then your other hemisphere can kind of take over and be dominant for that period of time when you're having a seizure. You would probably still notice that you'd be having a seizure, but it wouldn't be nearly as bad as when it spreads to both hemispheres. So this is rare as well, and we're going to look at a video of an individual named Joe who actually had that surgery and successfully treated his epilepsy. All right, so imagine this is Joe. He's got no corpus callosum. We ask him to draw these two shapes at the same time. So bimanual symmetric movement, that's easy for him as easy it is for us. But the neat thing is that when we give him two different shapes to draw at the same time, he can do that really well. It's not perfect. There is still some spatial temporal coupling, but notice how good those shapes are compared to someone who's neurologically tagged with a corpus callosum. And the logic here is that the corpus callosum, when it exists, when you prepare a motor program for one arm, some of that motor command crosses the corpus callosum and confuses or gets in the way of or causes spatial temporal coupling of the motor program for the opposite arm. So if we have these two motor programs and they're different, you know, one arm needs to do this, the other arm needs to do this, those motor commands cross the corpus callosum and interfere with each other. With someone like Joe, no corpus callosum, he generates those two motor programs, they don't interfere with each other, and he can send them out with less spatial temporal coupling than we see in us. Kind of an interesting finding. There are also individuals who have a larger corpus callosum than average, and when we ask them to do this sort of task, we actually see more spatial temporal coupling. So really good evidence that the corpus callosum is one neurophysiological source of spatial temporal coupling. Let's take a look a video here about Joe. And Joe is fascinating, not just because of his reduced spatial temporal coupling, but other behavior that shows the dominance of our left and right hemispheres for different tasks. And before you watch the video, I just want to remind you of some of the important things we'll see in this video. We will see him drawing two different shapes at the same time, as demonstrated here, but they're going to do some other fun tasks. And to understand these, remember that the left hemisphere, for most right-handed people, like Joe, language is dominant and object recognition is dominant. In the right hemisphere, face recognition is dominant, and this will be important in some of the tasks that they're going to give to Joe. But after the video, we'll go over a few of the examples that we saw. All right, let's look at some of those tasks. This is fascinating. So we've got Joe, right? No corpus callosum. We're trying to demonstrate that here. And one of the things they did is, as he looked at a fixation, they flashed the word up ship to the right visual field. Now from our modules on vision, we know that if something appears in the right visual field, it's going to end up in the left primary visual cortex. So that word ship will be seen by only his left hemisphere. Now, that information in the left visual field can go up to the language area of his brain, and he can say, I saw the word ship. You know, he can say ship. And that's kind of the same thing that would happen if you had a corpus callosum. Now here's the weird condition. Now we're going to flash up the word phone to the left visual field that will make its way to the right primary visual cortex. And notice, for us, that information would then cross the corpus callosum, and we could, to our language areas and say the word phone. But for Joe, that visual information is trapped or restricted to his right hemisphere. So we can say, what did you see? And he can't say the word phone because this information can't get to his language area without the corpus callosum. But interestingly enough, we can say, well, Joe, use your left hand, which is connected to the right hemisphere, to draw what you saw. And he'll start to draw a phone, and he'll be looking at his drawing with both eyes, so that information, the picture, will end up in both hemispheres. And now that it's in the left hemisphere, it can make it up to the language areas, and he can say, well, what I'm seeing myself drawing is a phone. So very bizarre. Okay, lastly, let's look at when they showed him these fun paintings that, for us, when we look at them, we can tell that there's a face, and the face is made out of objects here. We'll stick with the one where the faces are made out of flowers. So for Joe, he's looking at the fixation. We put this image up in his left visual field. That will go exclusively to his right cortex. And here, remember, the right hemisphere can recognize faces. So if we ask him what does he see, and we'll ask him to point with his left hand, because it's connected to his right hemisphere, he will point to face. He says, well, my hemisphere knows that it has seen a face. Same painting now, but we're going to put up in the right visual field. That goes to his left hemisphere. And now, if we ask his right hand to point to what he saw, he'll point to flowers. Because now, this hemisphere can't recognize faces, but it can recognize objects. So now all he can see are the flowers. So it's kind of neat. When we look at these, we see both things at the same time, faces and flowers, and we maybe focus on one more than the other, depending on what we choose to focus on. But for Joe, when we flash these up briefly so that it only goes to one hemisphere or the other, he can literally only see one thing at a time. So lots of stuff there about the corpus callosum, but remember, the main thing was that without a corpus callosum, we have much less spatial temporal coupling. Sort of flashed by a bunch of slides there. But I couldn't help but show that video because it's really neat, and some of the other things we learn about the dominance of the hemispheres for other tasks, like recognizing faces and objects, and also that language in almost all righties is dominant in our left hemisphere. Okay, that was our module on coordination. I hope you enjoyed the combination of a bit of cognitive psychology and a bit of cognitive neuroscience. So go through those practice questions, do some good studying, and when you're confident with the material, I wish you the best of luck with the test. And I'll see you in our next module, which I think is the last, and will be on motor learning.